This theorem is technically something we've discussed briefly before, but we've not talked about it in this way, nor written our answers the way we'll be writing them today. The intermediate value theorem is confusing sounding, but it's really quite simple. The basic example of this I can ask you, and I think it's the same example I used way back when we talked about it. When you get up in the morning, let's say it's 60 degrees. Right now it is 73 degrees. At some point, has it been 70 degrees? Yes, because it started at 60, and if it's now 73, at some point it had to be 70 degrees because it's in between the two values, correct? That's the intermediate value theorem. But we're going to talk about it in a very complex way with a lot of mathematical writing. So the intermediate value theorem, specifically for continuous functions, which we've discussed continuous before, says that a function, f of x, that is continuous on a closed interval between a and b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 is equal to f of c for some c in a or b. Again, that's a really fancy way of saying if when you woke up it was 60 degrees and right now it's 72 degrees, at some point it has been 70 degrees because it's in between the two. But we're going to have to discuss this using kind of like with continuity where we had 3 requirements. There are 3 requirements or 3 steps to proving things by the IVT, the intermediate value theorem, and that's what we're going to be doing today, is justifying our answers. But the way that you do this, to justify that f of x is equal to some value, 70 degrees, for some time or some x value on a certain interval, you do the following. Number 1, you have to show that the function is continuous. Now, we've talked about continuous, and there are some leeways we can take with continuous here. If it is a generally continuous function, like a linear function, a quadratic, a cubic, a quartic, those things that are straight up linear equations when we discuss them in the basic format, you can just say they're continuous because they're cubic, or they're continuous because they're quadratic. The only ones that we're going to have to go into more detail on this step is like piecewise functions, because we cannot guarantee they're continuous. We have to make sure there's not like a jump, that the points are the same. Number 2, you will show that the output at the first value of the interval is not the same as the output of the second value. So essentially just making sure that the outputs are literally not equal to each other. So we'll be finding those outputs and making sure they're not equal to each other. And then number 3, we're going to state that the value we care about, k, is in between those two values. If all 3 of those requirements or those steps we can meet, then we write the conclusion statement, and we are going to practice using the mathematical vocabulary like in the symbols that mathematicians use. This is how you will write most of your answers, and it's pronounced like this. Therefore, there exists a number x on the interval from a to b such that f of x is equal to k due to the intermediate value theorem. Mathematicians are lazy. We've made up symbols for almost everything. The backwards E, if you want to write that down, the backwards E stands for the phrase, let me scoot over, there exists. So we know the 3 dots is therefore. The backwards E is there exists a number x on the interval a to b, the st such that f of x is equal to k due to the IVT. Bless you. So you could write out those words if you want every time, but that's annoying. So you can use the mathematical symbol for those phrases that are used a lot in math statements. So they've created a symbol for them. Okay, so an example of what this might look like, and I've like given you some steps. So this one's a fill in the blank, and then we'll start writing it all fully ourselves. It asks you to show that g of x, which is equal to x cubed plus 2x minus 1, has a 0 on the interval between 0 and 1. Okay, our function we're dealing with this time is g of x. That's the function we're going to be using. The interval is from 0 to 1. So this is a, and this is b. That's the interval. Those are the x values that we're using. We don't care about what's happening on the other sides. We're just looking at the interval between 0 and 1. And we want to know if there is a 0 for that function. What does it mean for a function to have a 0?
There's a hole in it.
Not a hole.
It touches the x.
It touches the x-axis. It's an x-intercept. Or essentially that the output is equal to 0. So we are trying to show that for some value on that interval for that function, that it crosses the x-axis. We do that in 3 steps. Number 1 is to prove that it's continuous. What kind of function is g of x? Cubic. Cubic functions are continuous. We don't have to prove anything about that. We know that fact about cubic functions. So we can say g of x is a cubic function, therefore it is continuous on the interval from 0 to 1. There is nothing between 0 to 1 on a cubic function that will have a break, a hole, or some sort of disjoint. It's a smooth function. That's number 1. So again, number 1 is really easy if it's like quadratic, if it's linear, if it's cubic. Those are continuous functions. The only time number 1 gets weird is if it's piecewise or rational, because those have breaks in them. For part 2, we need to know the values at the beginning and end of my interval. So that means I'm plugging in 0 and I'm plugging in 1. If I plug in 0 to this function, it's going to be 0 cubed plus 2 times 0 minus 1, which 0 cubed plus 2 times 0 minus 1 is equal to negative 1. If I plug in 1, this is going to be 1 cubed plus 2 times 1 minus 1. 1 cubed is 1. 2 times 1 is 2. 1 plus 2 minus 1 is 2. So I got, when I plugged in a, which was the first value on the interval, I got negative 1. When I plugged in the end of my interval, b, I got 2. Are those the same number? Great. That's enough for part 2 just to say that they are not equal to each other. So after we show what a, or g of a is and g of b is, we say, therefore, g of 0 does not equal g of 1, because they're not the same number. Yes? Now, the number we're trying to make sure exists on this interval is the number 0. Is 0 in between negative 1 and 2 on a number line? Great. So we can say the statement that g of 0 is less than 0, which is less than g of 1. Essentially saying 0 is between the 2 values I got, because it is. 0 is between negative 1 and 2. Since I got through all 3 requirements, we say, therefore, there exists a number x on the interval 0 to 1 such that g of x is equal to 0 due to the IVT. So the things you'll be replacing in this conclusion statement over and over again is the interval. Those numbers will change for each problem. The value you're looking for is going to change for each problem, as well as the function name. Sometimes it's f of x, h of x, whatever. But the rest of that is pretty much going to stay the same for the conclusion statement. So this is just like continuity, where we have to write the 3 things out, but they're different 3 things.
If it did equal, it would just stop right there, right?
Yeah, if the numbers equaled each other, you would stop right there and you'd be like, I can't prove this because part 2 fails. I can't use the IVT to tell you this. And if it fails on part 1, like it's not continuous, you stop on part 1. It's not continuous, I can't use IVT.
Is there a way to write it?
The questions would probably be like, can you justify it? And you would say no, because 1 fails. Or no, 3 fails. Can we start this next example?
No.
Yay, we're gonna write the whole thing this time. So use your nice, neat handwriting. I gave you a lot of space, but we'll do our best. Okay, it asks you, must there be a value x for the function f of x equal to this piecewise function, x squared minus 4 and 4x minus 7, on the interval from 0 to 3 such that f of x equal to negative 1. Okay, so we have the function that we're checking, we have the interval that we're checking, and we have the number we want to see show up. Okay, first step is to make sure it's continuous. Now this is what kind of function? Piecewise. For a piecewise function to be continuous, we need to make sure that on that interval between 0 and 3, that there are no breaks in the graph. The way we do this for a piecewise function is we say, okay, the first piece is all before 1. What kind of function is before 1? What kind of function is this? Quadratic. Are quadratics continuous?
Yes.
Okay, great. What kind of function is after it? Linear. Are linears continuous?
Yes.
So we just need to make sure when it shifts from one function, the quadratic, to the linear, that it's still continuous. So we go back to the original 3 steps for continuity. Those 3 steps are, number 1, does f of negative 1 exist? So we do negative 1 squared minus 4, which is equal to negative 3. So it does exist. Okay? The second requirement for continuity is that the limit exists. So we check the limit as x approaches 1. Why am I checking it at 1 and not my interval numbers? Yeah, that's when the function changes. Okay, I'm looking at this right here. It's when it changes from the quadratic to the linear. So I have to check that point when they change from one to the other. So I'm going to check the left side, which...
I have a question. So essentially with this, you're basically doing like a mini check for each one, right?
Yes.
Okay.
Yeah, if this were a regular function, all we'd have to say is it's cubic, done, it's continuous. But this is a piecewise function, so I have to make sure that when it changes off from one number to another, or one function to the other, it's still continuous. On the left side, when you plug in 1, oh, I totally just did this wrong. Not super wrong. We shouldn't be plugging in negative 1. We should be plugging in 1 in this problem. It's still negative 3. That number didn't change. I just went through the whole spiel of why you pick 1 and pick the wrong number. It's fine. When we plug in 1, on the left side, that's what we just did. We'd get negative 3. When we look on the right side of 1, that means we're plugging it into the linear part. But what's 4 minus 7?
3.
Negative 3. So if my limit is the same on the left and the right, what's the conclusion I draw? What?
Therefore, negative,
The limit.
f,
Keep going.
f of x equals to negative 1, no, negative 3.
Yes. So if the number is the same on the left and the right, then the limit is that number. The last step for continuity is just that steps 1 and steps 2 match. The number I got in step 1 is what? The number I got in step 2 is what? Okay, so we're good. So we write the statement, the limit as x approaches 1 of f of x is exactly equal to f of 1. Therefore, and I'll write this in red because it's kind of the end here. Therefore, f of x is continuous on the interval from 0 to 3. I only had to check the number 1 because that's where the two continuous functions, a quadratic and a linear, which you guys told me are continuous, exchange. So I check that number just to make sure it's still continuous there. Therefore, it's continuous on the entire interval if I have a continuous function and a continuous function.
Yeah, what's that? Theorem writes down.
Yes.
What do you mean I'm trying to do? I can't write small.
Where'd we get what from?
Yeah.
The 0 and 3? Great question. That's the interval from the original question. I know that everything before 1 will be continuous because you guys told me it's quadratic. I know everything after 1 will be continuous because it's linear. I just needed to make sure at 1 it was still continuous when it exchanged. And it is, so we're continuous on the entire interval. So we've shown that it's continuous on this interval. Now we just need to do step 2 and step 3. Step 2 is to plug in the first value in the interval. So we're plugging in f of 0. And for a piecewise function, we have to make sure we're plugging it into the correct part. So what part of the equation, the first part or the second part, the quadratic or the linear, will we plug in 0? The quadratic, because that's where it is in its domain. So that's 0 squared minus 4 or negative 4. We're plugging in 3 because that's the other part of the interval, the end of the interval that we care about. Which part of this piecewise function am I plugging that one into? The linear, because 3 is bigger than 1. So 4 times 3 minus 7, that's 0. Are those the same numbers? No, pretty obviously negative 4 and 0 are not the same.
Miss, I think your math is wrong. 4 times 3.
Oh, that's super embarrassing. I added 4 plus 3. That should be 5. It sure says 5 on my key right here, and I just did that math wrong in my head. Thank you. But are negative 4 and 5 the same number? Great. So we can conclude that f of 0 is not equal to f of 3, which is what we have to show for part 2. Just literally that they're not the same value. The third part of this is just showing that the number we care about, the number we want to prove or show that the function can reach, is in between those two numbers. Look back at the question. What are we trying to show the output? Negative 1. So we want to make sure that negative 1 is between these two numbers. But isn't negative 1 between negative 4 and 5?
Yeah.
Great. So we can say that f of 0, which is negative 4, is less than negative 1, which is less than f of 3. That's saying negative 4 is less than negative 1, which is also less than 5. That's a true mathematical statement. And since I got all the way there, we write our final conclusion statement saying, with mathematical symbols for everything instead of words, oh my gosh, come on. Therefore, there exists a number x on the interval from 0 to 3 such that f of x is equal to, oh no, it didn't stick. Is equal to negative 1 due to the intermediate value theorem. So just like with continuity, we do have to show all three parts. But for, like I said, like 97% of these problems, part 1 is just stating it's continuous because of the type of function that it is, just like we did in that first example. Make sense? Cool. Let's see a few more examples of ways you might be asked about this. This problem C is a very AP style question. So if you're going to be taking an AP math class, this is the way a lot of the questions for this unit would be written. I don't know why I haven't shifted it over. It says a car travels on a straight track during the time interval from 0 to 60 seconds. The car, the var, that should say car. The car's velocity v measured in feet per second is a continuous function. The table below shows, oh my gosh, that should say shows. It was actually, well, it was a Tuesday, but it was yesterday being a Monday on a Tuesday. Does that still count?
Yeah.
Okay, great. It's embarrassing. Shows the selected values of the function in the table. Great. The question is, for time 0 to 60, must there be a time t when v of t is equal to negative 5? Now, I'm sure you're thinking, when would velocity be negative? It's a great question. When you learn more about calculus, negative velocity means it's going left. Positive velocity would mean it's going right. because velocity is just speed with direction. So positive and negative is directions. Anyways, I digress. We need to show this. Okay, let's just make sure we know what it's asking. It's saying somewhere between time 0 and time 60, will the car be at -5?
Yes.
Why?
Because it has to go somewhere, it has to get up to 10.
Yeah, if it's at -10 here, and then it's at 10 here, at some point it passed -5, right? Like that makes sense to us. Great. You understand IVT in your brain, we just got to write it correctly. So the first step is to show it's continuous. What kind of function is this? Does it tell us it's like cubic or anything? No, but what does it say about it? It tells us it's continuous. Great. So you just literally get to say that. You say v of t is continuous. Step 1 done. It was given to us in the problem. We just have to restate it as part of IVT. Step 2 is to talk about the beginning and the end of the interval. At the beginning of the interval would be v of 0. What is the value v of 0? -20. You read it straight out the table. At the end of the interval, at 60, what is v of 60? 10. Are those two numbers the same number? Great, so we can say, therefore, v of 0 does not equal v of 60. They're not the same number. Part 3 is just to show the number we care about is between those values. What number do we care about again? -5. So all we have to say is v of 0, which is -20, is less than -5, which is less than v of 60, which is 10. -5 is between those two numbers on a number line. -5 is not between -20 and 10? Okay, great. Therefore, there exists a number, t, we're not using x's this time, on the interval from 0 to 60, such that v of t is equal to -5 due to the IVT. So IVT, like I said, it's a simple concept. We were all pretty much able to tell, well, like, duh, it has to reach -5 at some point if it went from -20 to 10. But to show me is the 3 steps. Does that make sense? Okay. For the examples below, we're going to use this graph of the quadratic function h that shows the height in feet of a rocket from the ground t seconds after it was launched. So if we're just looking really quickly at the picture of the rocket, it goes up, it comes down. That's what rockets do. They go up, they come down. Okay. Letter A says, can you use the IVT to show that on the interval from 1.5 to 6, that the rocket reached its maximum height of 225 feet? If yes, justify it. If not, explain why. Okay. At time 1.5, what is my height?
1.4.
At time 6, what is the height?
1.4.
So are those the same number? So can we use the IVT at all? No, we can't use IVT because requirement 2 is going to fail. F of 1.5 is exactly equal, oh, it's not F, it's H. H of 1.5 is exactly equal to H of 6. So even though I have the graph, and I can obviously see that the rocket's going to reach its maximum height in between those two numbers, I can't use IVT to tell that, because the only thing I know about IVT is at the beginning, it's at 144, and at the end, it's at 144. Does it go up? Does it go down? Does it stay in the middle? Because we're only using IVT, we can't prove it. Does that make sense why we can't use that? Okay, even though it's continuous, part 2 fails. Part B says, can you use the IVT to show that on the interval from 0 to 4, that the rocket reached the height of 144 feet? If yes, justify it. If not, explain why. So this time we're working on the interval from 0 to 4. And if we read the graph, 4 would be here. On that interval from 0 to 4, would we be able to use IVT to show that it reached 144 feet?
Yes.
Yes. Okay, let's do it. What's the first requirement for IVT? What kind of function is this when a rocket is launched? It makes this shape?
Oh, quadratic.
It's a quadratic. So we would say h of t is a quadratic. Therefore, it is continuous. That's enough to know that it's continuous. Quadratics are continuous.
Okay, all of them?
All of them. Unless it's part of a piecewise function.
So like 2, 4, 6. Why is it 6? Quadratic?
6 would be it doesn't have a name. It's a power 6. Yeah. Part 2 is supposed to talk about the beginning and the end values. So I need to know what h of 0 is. Well, what's h of 0?
0.
0. And then I need to know h of 4, which is 225. Are those the same number? No, therefore, h of 0 does not equal h of 4. So we can keep going. And in part 3, we just need to show the number we're caring about is in between those two values, which it is, because 144 is between 0 and 225. So we say h of 0 is less than 144, which is less than h of 4.
Is there like a way to make an abbreviation to that one?
No, that's already about as shortened. So we say, therefore, there exists a value t, we're using time,
Oh, right.
on 0 to 4, such that h of t is equal to 144 due to the IVT. Yes?
Where do I get the Hoover?
Now I'm adding this question back in here because on our test we took last time, the average rate of change question stumped just about everybody. We need to practice some average rates of change. It says, what is the average rate of change between time 0 and time 6? That just means I'm trying to find the slope between the point on the graph at time 0 and at time 6. Another way this question could be asked, and I would probably write this down, is it could ask you, what is the slope of the secant line, not trig secant, but geometry secant. What is the slope of the secant line between those 2 points? That's another way this question could be asked. And so we just want to know the inputs and outputs at those particular values. Average rate of change formula, which you have notes over this, is the change in the distances, or in this case, the height. So it's going to be the height from time 2 minus the height from time 1, absolute value, all over time 2 minus time 1. Okay. What is the height of the graph at time 6? 144, right? What is the height of the graph at time 0? 0. Time 2 was 6. Time 1 was 0. 144 minus 0 is 144, and the absolute value of that is still 144. So this is just 144 divided by 6, which if you do that math real fast, it's going to be 24 feet per second. That's the average rate of change or the slope of the secant line between those 2 points if we were to draw a line between 0 and 6. One more review question. It says, what is the limit of the graph as t approaches 6? So if we go look at 6, oh, lost it. For a limit to exist, it has to be the same on the left and the right. What's the limit as we get close to 6 on the left side?
Oh, 41.
144. What's the limit on the right side?
Oh, 45.
So what's the limit?
45.
144. So the limit as x approaches, not x, t approaches 6 for h of t would be 144. That's it. So again, the IVT itself, it's one of the big 3 formulas or theorems in calculus that kind of base the rest of calculus off of it. It's a very simple concept, but the way you write about it correctly does require a little bit of notation.